Great, this is neutralization reactions. An acid and a base are mixed together, a neutralization reaction occurs. For first year chemistry, we're going to stick with strong acids and strong bases. Second year chemistry, you'll be doing a strong acid with a weak base or vice versa. Titration is the method of determining concentration of an unknown acid using the known concentration of a base, or an unknown base using a known concentration of an acid. There are two types of neutralization problems. Type 1 is when they're asking you for the volume of the acid given the volume and concentration of the base, or they're giving you the molarity and volume of the acid and the molarity of the base and asking you for the volume. You are going to use what we used back in chapter 4 for dilution computation. It's the same computation. It's MAVA is equal to MBVB, which is molarity of the acid, volume of the acid will be equal to the molarity of the base times the volume of the base. So again, this type of problem is given when they give you 3 of the 4 pieces of information, something like 100 mils of 0.10 molar HCl and with 200 mils of a sodium hydroxide, and the question says, what's the molarity of the base? Plug everything into the right spot. Second type of problem for neutralization. When they give you the quantities of both the acid and the base, they give you the molarity and the volume of the acid and the molarity and the volume of the base, you're going to have to do a stoichiometric limiting excess problem. All right, strong acid, strong base titration. Titration usually involves delivery from a burette of a measured volume of a solution of known concentration. Usually for us, a strong base, sodium hydroxide, is in the burette, and a solution of an unknown acid concentration is in the Erlenmeyer. Volume is known of the acid, volume of the base delivered is measured, concentration of the base is known. So what you're usually trying to find out is the concentration of your acid. The end point or the equivalence point is when enough hydroxides from the burette have been added to react completely with the hydrogen ions in the acid to make water, leaving no more hydrogen ions in solution. The end point is usually indicated with an indicator that changes color. So for example, phenolphthalein is clear in an acid, pink in a base. So the minute it goes pink, you have reached the end point and you have a solution that has no more hydrogens in it anymore. For example, hydrochloric acid, which is a strong acid, and which is a strong base, react. This is called a metathesis or a double replacement reaction. And what happens is the sodium replaces the hydrogen, and the hydrogen replaces the sodium, and you get sodium chloride written appropriately. It's an ionic compound. Has to be equal to 0 plus 1 minus 1. You get a 0 and water. This is called the molecular equation, or ME for short. The complete ionic equation, or CIE for short, this is called complete ionic. Is you write out the strong electrolytes, you write out the electrolytes in their ion form. Electrolytes include strong acids, strong bases, and soluble salts based on solubility rules. Do not separate into ions, do not separate gases, solids, weak acids, weak bases, and water. So the complete ionic equation for the molecular is going to be hydrochloric acid is a Strong acid is a strong electrolyte, separates into its ions. Sodium hydroxide is a strong electrolyte, a strong base, separates into its ions. Sodium chloride is a strong electrolyte, but it's a soluble salt, so it separates into the ions. And water is not a strong electrolyte, it's not separated, it stays as one entity. Spectator ions are those ions that are on both sides of the arrow, same quantity, exactly the same ion. Notice sodium and sodium and chloride and chloride. Spectator ions cancel out, and the net ionic equation is only the ions involved in the reaction. So for this neutralization reaction, any neutralization reaction that is between a strong acid and a strong base will have this net ionic neutralization. Notice it is a 1-to-1 ratio. One hydrogen for every one hydroxide will produce one water. So if I want to neutralize 4 moles of the hydrogen ion, I need 4 moles of hydroxide. And I will make 4 moles of water. It's just stoichiometry. All right, so here's an example of one type of neutralization problem. We are going to calculate the volume of a 0.1 molar hydrochloric acid, which is a strong acid, needed to neutralize 25 mils of a 0.350 molar sodium hydroxide. There are 2 ways to do this problem. The easy way. You don't have to change the volume to liters. You can give your answer in milliliters. Molarity is going to cancel out. Volume of the acid is going to turn out to 0.5 milliliters. All right. Way number 2. The moles of hydroxide known is going to be the molarity. I have then 0.00875 moles of hydroxide. The moles of hydroxide to moles of hydrogen are 1-to-1. So if I have 0.00875 moles of hydroxide, I need the same quantity of hydrogens to neutralize. Therefore, I need 0.0005 moles of hydrogen. Moles per liter. Then figuring out volume, it'll be moles divided by molarity. I have my moles. And I have my molarity. I get 0.0875 liters, which is 87.5 milliliters, which is exactly the same. Right? Another problem. This one is giving me the volume and concentration of a base and giving me the volume and concentration of an acid and asking me what the pH is. This is going to be a limiting excess stoichiometry problem. So I am going to have to use stoichiometry to figure this one out. I am going to determine determine the number of moles of hydrogen hydroxide before reaction occurs. So how many moles of each do I have in the individual? From the nitric acid, I have 0.010 moles. From the sodium, 0.0150 moles. Don't really care about water. If you notice from the two numbers, this is going to make. He's the larger number. Do my calculations. This is going to be 0. This is going to be 0.05 moles of hydroxide left over. This is after reaction. In order to calculate the pH, I'm going to need to calculate the POH. And the POH will be the negative log of the hydroxide concentration. So I'm going to take the negative log of the hydroxide concentration in the mixture, and I have 0.005 moles of hydroxide in a total volume of 0.200 liters, which concentration of excess hydroxide of 0.025 molar. The POH then, log of it, which comes out to be 1.60, and pH will be 14 minus.